Ladies and gentlemen, this is the time to start new keynote, and we invite Professor Shuai for presentation of his lecture. You are welcome, Shuai.
Hello. Yeah. So we see each other again. Every year we have the
Yeah.
chance to see each other. All right. Should I start now?
Yeah.
All right. Hello everyone. It's my great honor to be here to deliver this keynote speech about our recent work on a new type of meta optimization approaches, which is called as computation of traps and cooperation of members algorithm, which is CTCM in abbreviation. This is a newly developed model by us, and we uploaded this model to the original version of this model is this mathematical model is written in MATLAB, and we provide a link here. If you have interest later, you can just log into MATLAB and download the code so that you can test it on your own computer. And also we created a discussion group so that if you have interest, you can also join this discussion group to discuss with some people who also have interest in this topic. All right, so basically this model is an alternative to PSO, which is particle swarm optimization, which is a dominating model in the area of model-free optimization. Particle swarm optimization and also similar to genetic optimization, which is quite popularly used for some optimization problems that you don't exactly know the model. And the original model is quite intractable to solve numerically. And it is a heuristic algorithm. For PSO, it is inspired by the swarm of particles. But here, the CTCM, the algorithm we developed here, it is inspired by the computation and cooperation behaviors of our ancestors in old days. The idea was for optimization problem, the basic idea is to try to search for the best variables that has the optimal solution. Well, there are many behaviors in animals or in human societies which bears similarity to this kind of behavior. For example, in all this, when primitive human, they are searching for the most fittest environment to live. They are trying to find a location for that particular location that has the highest reward to the survival of people. Therefore, in this sense, this kind of a searching behavior of human is similar to an optimization problem. Therefore, we are able to get some inspirations from this kind of human behavior to design a general optimization tool. This is basically the motivation for this study. Well, specifically for the human society, we observe, like the primitive human society thousands of years ago, we observe several behaviors, just as characterized by the figure on the right-hand side. We have several groups. We call it as traps. Each trap, actually, it is a human group. Inside this kind of group, people cooperate with each other. They are treated as the same family or the same society. They have cooperations to help each other so that they can maximize the reward for the whole society, the whole trap. But for different traps, they compete, they fight with each other. For example, if two traps meet with each other at the same location, they will fight, and the survival will keep staying in the original place. But the other one, the failure, the loser, they have to migrate to some other places. This is generally the behavior of human traps. And we abstract full representative behaviors from the old human society, which is cooperation, as mentioned inside the trap, that is cooperation. Computation, which is between different traps, people compete. Migration, and another one is conflict. When the two traps meet with each other at the same location, they have conflict. The fourth one is migration. Migration is saying that, okay, when there is a conflict between two traps, one have to, the successful one will stay in the old place, in the original place, while the other one, the losing one will have to migrate to some other places. This is what we call as migration behaviors. Well, like others, we have some mathematical model, but because of the time limitation, I'm not going to go through the mathematical model in details, but I will basically introduce a little bit about how did we find out this algorithm and what is the basic idea we have. Honestly speaking, this method is inspired originally by PSO, particle swarm optimization, but we realize one limitations of particle swarm optimization, which is like, simply speaking, there are two kinds of behaviors for the particles in PSO. One is that each particle is trying to go to the global best. Seeing the global best is that for each particle representing each sample of the data, each particle corresponds to a reward or the cost function or cost. Well, if we choose, we name the one with the best, the lowest cost as a global optimal. And then each particle for the next step movement, it has a trend to move towards to the global optimal point. This is the first behavior. The second one is that each particle has a memory. It remembers the global optimal it has already reached in history by itself. By saying by itself, it means that because each particle is moving. If we look back into the history for this particular particle, for all the places or for all the samples it has already experienced, there must be one point which is the best among all the peers. We call that one as a local optimal. Well, for each particle, the second behavior it has is that to tend to approach to the local optimal. And definitely there are some additional randomness mechanism, but overall, based on the two behaviors, the location of the particles evolve. And finally, it drives the system to the global best point. But because the global optimal point is driving all the particles to move, because each particle has a behavior to go to the global optimal. Therefore, in the end, the behavior of particles is that they trying to converge to the together, meaning that around some points, there is a cluster of points, particles, which is quite close. The reason they go their particular location is that they think that is a global optimal. But the drawback for this kind of behavior is that it loses some diversity. We don't need so many particles to go exactly to that place. We expect some particles go elsewhere to explore better about some unexplored environment. Motivated by this kind of thing, we are thinking that is that possible that we cut the groups, the whole group, the total, supposedly we totally have n particles. Can we cut partition n into several groups, which is corresponding to each trap here? Well, inside each trap, we have this kind of evolution. But in order to avoid all the particles go together, we generate some repulsive behaviors between different traps so that we can maintain a kind of diversity. This is our original idea. But we tested that if we use a simple strategy to simply use the repulsive forces, the drawback is that because of the repulsive force, some particles, although they have been in a good position, good location, but due to the repulsive force, it might go somewhere away from the best location, which inspires us that the repulsive force must only be effective to those non-favorable particles. For those which has already get a good reward function, we are not expected to apply this kind of repulsive force to that. Therefore, instead of directly applying the repulsive force, we introduce a behavior of migration and conflict. When two traps have conflict, we compare, each trap, they have inside each trap, there is one particle which has the best performance than the others inside this trap. And that one can be used to represent the whole trap. And when we compare two traps, we are comparing that two individuals. And if we say one trap is better than the other trap, we mean that best particle inside this trap is better than the best particle in the other trap. Well, if this kind of situation happens, we expect the winning trap will stay in the old place, maintain its location, but the other losing trap will have to migrate, which means that this is not bilateral force. This is a unilateral force. Well, how can we design the conflict? What do we mean by the conflict? Which specific trap has conflict with another? By defining the conflict, we mean each trap randomly select another trap and then have conflict with the other one and to compare with the other one and then generate this kind of migration behavior. Due to this kind of design, for the globally winning trap, it will never be affected by the migration behavior because it is always the winning group. Migration is only affects the motion of the losing traps. For the globally best trap, it never gets influenced by the migration behavior, which means that for the winning trap, it's kind of like running the PSO behavior. But for those losing traps, they are trying to avoid the winning trap so that we can maintain diversity. In the meanwhile, they have certain PSO mechanism to optimize their solution so that we are more likely to find the global optimal than existing PSO. So we have some detailed explanation in the paper and in the slides about this kind of a behavior designed. How do we formulate as mathematical formulas to move the particles? We also did some preliminary computational complexity analysis and convergence analysis. But anyway, I'm going to show this part about simulation results. Actually, we extensively run this algorithm on some benchmark problems. There are many functions provided by the CET package. And we compared with many functions provided over there. And as you can find that the red line represents the best solution has been found so far in a specific iteration. And we compared with other methods as listed here. As you can find that this new algorithm convert very fast and more accurate than existing ones. And to conclude, Here we presented a new um, uh, meta optimization algorithm, which is model free. You don't need to know the model itself. You only need to know the input output. And we compared, it is an alternative to a genetic algorithm, alternative to a PSO, but it is more powerful in the sense that it is faster and it is more accurate. And for technical details, you can refer to our publication. Well, for the interpretation on why it is powerful and why it is able to generate a better behavior, as I explained here. The main reason is that we are designing a mechanism so that we can avoid the degradation of the diversity of particles in PSO. That is why it is able to outperform others. Thank you very much. Questions or comments?
That's all presentation.
Yes.
Actually, we expected 45 minutes lectures.
Yeah, I would like to leave more time for the question and answer if there are. Because, you know, there are many technical details I didn't go through because I think I want to just share the basic ideas here so that you can better understand that.
Well, dear colleagues,
Yeah, please.
a lot of time to ask.
Yes, yes.
Thank you very much for presentation and for new approach in optimization. So my first question is how you can prove that this idea can be implemented in many different cases. Maybe just some special test functions when you can outperform all algorithms. This new algorithm look like standard PSO. What is a general idea why it outperforms other approaches?
Yeah, right. We are not confident that it is always outperform others. There must be someone which is better, or not, if not at present, but definitely in the future. But the reason that we are confident that this is better than some existing algorithm is that it introduces a new mechanism to avoid the degradation of the divergence of particles in PSO. This is a key message I want to deliver for this method. Because the reason, you know, sometimes when PSO go into some local optima, one important reason is that if one particle, if so far, okay, we have 10 particles, for example, if one particle find a local optima, in the sense that this particle, the objective function is lower than all the others. Okay, all the other particles is trying to go to that particular place. And unfortunately, if all the other particles has already been in that particular place, they have no chance to escape because locally they feel this is the best. This is a kind of loss of divergence. Well, in our mechanism, due to the introduction of the migration behavior and the conflict behavior, if there has already been one particle in a specific location, there is a kind of a repulsive force applied to other particles to further go into that place, so that we can make sure that the particles will not be crowded into one specific place. This is basically the idea why it can avoid the degradation of diversity and make it more efficient.
For me, it looks very similar to multimodal optimization, different sharing methods or crowding distance methods. So in these methods, you can use standard approach like PSO or differential evolution, but the same, you just don't give a chain solution to together in one place. You have some penalty for this and so on.
Yeah.
Okay, it's very interesting idea. Thank you.
in terms of this point, I would like to emphasize one more thing. You know, for many situations, the reaction or the a kind of effect, it is a bilateral in the sense that, okay, for example, if I give you a repulsive force, you also apply the same repulsive force to me. But in our situation, our reaction or influence, it is a directed, not one directional, not two directional, in the sense that only the winner generate an impact to the loser, so that the loser will not come here to this place, but the winner will not be repelled from its old place.
Yeah.
Thank you.
May I ask?
Yeah.
May I ask the question? Yeah.
Yes,
Have
please,
a
please.
questions related for my sphere of interest about large-scale global optimization problems. What was the maximum number of variables? I mean, in the benchmark problems, you evaluated your algorithm. Maybe you, let's say, faced with the limitation after up to 100 variables, after 500. Yeah, something like that. Yeah, please comment.
Honestly speaking, this is this work is recently still under review, the second round of review for a journal publication. In our initial study, we didn't do like two high-dimensional problems. But one thing that I can claim here is that for any places, any of problems that can be solved by PSO, I mean the scale of the problem, if PSO is able to deal with like 10,000 variables, okay, this method is able to deal with 10,000. That is first thing. The second thing is that in that kind of situation, I can surely claim that this method in the same scale of the problem, it can outperform PSO.
Okay, yeah, thank you. Thank you.
Yeah, Alex, any question? Okay, I have a question.
Yeah, please.
Relativity, such a modeling of society. Why only chief and others? Because in many cases we have such an hierarchy. For example, chief for peaceful time, chief for military, chief for hunting, and let me say, I don't know how to say, sub-chief, something like that, to be chief when chief is out, and so on. Much more sophisticated social cooperation could also be used, not?
Yeah, exactly. As you said, that human society, real human society, is hierarchical, layer by layer, and like a pyramid, right? But in our model, we only consider two roles in each tribe. One is the chief. All the others are the same. Well, the chief is think about all the societies of human. The chief is supposedly to be the most smartest person or most successful person. Here, the chief is the particle which has the best solution. And the meaning of the chief is that the chief has certain characteristics to represent the whole society. Because here we need to define, like when the two tribes compete, what do we mean by two tribes compete? How do we define which tribe is successful or which tribe is losing? We have to find one particle to represent the whole tribe. Therefore, we define a role which is the chief. The chief is a particle which is the best inside this tribe. And when we define the properties of a tribe, we are using the properties of that specific individual to represent this tribe. This is the basic idea. But I totally agree with you that maybe by introducing more advanced structures of the society, like a hierarchical, it might further enhance the performance of this algorithm. I totally agree with you.
Yeah, I see. But there are also, how to say, other kind of social behavior. For example, in old time, women were responsible to keep good solutions. Men were responsible
yes.
to find other solution, maybe better, maybe worse. And
Yeah.
it also can be modeling if we are modeling as a society.
Exactly, perfect. I like your idea. Yes, I think although this is a social science, but I believe every social behavior, there must be some reason. There must be some mathematics. And I agree with you that for societies, the reason that it evolves into the situation, it includes male and female with different social roles. There must be some reason. By taking that into the modeling, it must be able to enhance the performance.
Yeah, but nevertheless, you are modeling competition of tribes when they are going to one place and there is such a pressure between them. But for example, one tribe could, how to say, contain more fighters.
Yeah.
Another one more contain more hunters and so
Right.
on. It also can be, how to say, organized such a sophisticated
Right.
development
Right.
of the group.
Yeah. I think this model may have at least two possible kind of applications in the sense that the first possible application is that we use to optimize engineering problems. The second one could be if we model it better to mimic the real human society, it may help us to interpret some behaviors in the human society, which might also be very impactful. So therefore, from the audience, if you have interest into this topic, we put the email address here to the lower left corner. You can send emails to us so that we can study these behaviors together and make the model more interpretable to more behaviors.
Okay, I see. Thank you very much for answers.
Thank you.
Ladies and gentlemen, any other questions, please?
Yeah, any other questions, please?
Yes, I would like to.
Yeah, please.
What about tuning of parameters for this algorithm? The number of human and number of tribes, and also what about distribution you use for
Perfect question.
random variables?
Yeah, I like your question. Actually, again, because this method comes from PSO and modified from PSO, therefore, PSO is a parent of this algorithm. Therefore, the tuning algorithms for PSO is also applicable to this algorithm. This is the first point. The second point, there are some new elements in this algorithm which was not adopted from PSO. Therefore, it needs tuning, like the number of traps. But the number of traps, it is like the basic rule of thumb is like initially you can choose for example, let's maybe firstly we think about the extreme situation. When there is only one trap, it is equivalent to PSO. When there are two traps, because the two traps will stay away a little bit from each other. If each trap has already, think in this way. If we want a trap to go to the optimal point, because here each trap, inside each trap, it's running PSO. Therefore, for the winning trap, the behavior is the same as PSO. Therefore, for the simple trap, they will not maintain the diversity. They will go as a cluster to the global optimum. Which means that if I want maintain, how do we define the diversity? The diversity can be defined in this way. If I only want 10 particles to go to the same place, this is a kind of definition of the diversity, meaning that for 11 particles, okay, one must stay away. Then I can just put each trap has 10 members. And if I totally have 100 particles, then I partition into 10 groups. This is the idea. And another thing I would like to emphasize here is that, think one kind of scenario. If we are running PSO, we have several ways to run PSO. We can run PSO once. Okay, we get a good point. And then we rerun PSO and run it 10 times. Okay, one PSO algorithm, same PSO algorithm with the same setup, but repeat it for 10 times, we get 10 different solutions because our initial setup could be different. Then compare this situation with the situation that we put supposedly in each particle run, we have totally 20 particles. Then in summary, in total, 20 particles in each run, and totally we have 10 runs, we have 200 particles. Instead, if we run our algorithm with totally 200 particles, but with 10 groups, each group have 20 particles, what will be the consequence? Which one is better? The first situation, we rerun the PSO for 10 times, and we pick the optimal among all the simulation runs. That is one situation. The second situation is we only run once with our algorithm. The conclusion will be our algorithm will be better. The reason is that each time you rerun that, it has the same chance to go to the same local optimal. There is no systematic mechanism to generate a repulsive force from the local optimal. But this new algorithm has this kind of mechanism. Think about in many situations for the users to use PSO. In order to get a good result, they repeat their simulation for many times and pick a good starting point, a good initialization, so that they can come out with a good final result. But that is not as effective as here, because every time you restart it, you rerun it, there are many things to be repeated. But here, we maintain the diversity. The key point here is maintain the diversity.
Thank you very much. It seems very promising.
Yeah. Feel free to download it because we have already uploaded the code and some
It will be very
tutorials on
interesting
this
to
method.
try it in high dimensions.
Yeah, right.
Sparse space. That's to find these different places where you put drives. Okay,
Yes.
it's very interesting. Thank you very much again.
Thank you.
Okay, dear Shuai,
Yeah.
thank you very much for interesting
Thank you. See you guys
presentation
next year.
and discussion.
All
Thank
right.
you very much.
Thank you.
Yeah.
All right.
Okay,
Have
dear
a good day.
colleagues, we have additional time. I would suggest to have a rest 10 minutes and then start the last session earlier than it is planned, because presenters are here and they can present their talks earlier. Alternative is to have rest half an hour and continue according to the schedule. Any reaction, please? Okay, in this case, let me say I ask your advice, and after that, I decide. Now we have 10 minutes interval to have a rest, and then 15 minutes before schedule, we'll start our last session.